There is a powder that costs $2 and makes any concrete structure stronger with every passing year, not stronger for the first decade before it starts cracking, not stronger in the lab before weather and seawater get to it, stronger every year for 2,000 years, without maintenance, without repair, without a single structural engineer's intervention. The concrete that built the Pantheon in Rome has been exposed to the full force of Italian weather for 1,900 years, and its dome is still standing, crack-free, without a single structural repair in its entire history. The concrete piers of the ancient Roman port of Caesarea Maritima have been submerged in the Mediterranean Sea for 2,000 years. And a 2017 study found that the seawater exposure had not weakened them. It had made them stronger. The seawater was still growing new crystals inside the concrete matrix, deepening the bond between the aggregate and the binder, tightening the structure from the inside out. 2,000 years of continuous seawater exposure. And the concrete was getting stronger. The modern Portland cement industry generates over $600 billion in annual revenue. The concrete produced from Portland cement begins deteriorating from the day it is poured. It develops microcracks within years. It fails structurally within decades. Major infrastructure built with Portland cement requires complete replacement every 50 to 100 years. Highways, bridges, seawalls, foundations, all of it. Replaced, on schedule. Generating the construction contracts, the materials purchases, and the engineering fees that the Portland cement industry's entire business model depends on. A $2 powder that makes concrete stronger over time rather than weaker, that lasts 2,000 years rather than 50, and that cannot be patented because the Romans used it before patents existed, is not a market opportunity for that industry. It is the most direct threat to its replacement cycle that has ever been documented. The powder is volcanic ash, specifically a naturally occurring pozzolanic material called pumice, or volcanic tuff. And this is the story of the building material that made Roman civilization's infrastructure last 2 millennia, and that the Portland cement industry buried the moment it calculated what infrastructure that never needs replacing would do to its revenue. Welcome to Forbidden Camping. Subscribe and hit the bell right now. This channel opens the vaults they spent fortunes locking. Now let me take you back to where this all begins. Let me take you back approximately 2,000 years to the volcanic hills south of Rome near the town of Pozzuoli. The Romans had a problem. They needed to build underwater. The harbors, seawalls, and breakwaters their expanding maritime trade empire required had to be constructed in seawater, and every building material available to them failed in seawater within years. Stone crumbled, lime mortar dissolved, timber rotted. Then a Roman engineer working near Pozzuoli, sometime in the 2nd century BC, discovered that the gray volcanic ash deposited by the Campifli volcanic field had a remarkable property. When this ash was mixed with seawater and lime, it set hard underwater. Not crumbled, not dissolved, set hard. Harder than the stone the Romans were building on. They called it pulvis putillanus, the dust of Pozzuoli. We call it pozzolan. By the 1st century AD, Roman engineers had developed this material into the most sophisticated concrete technology the ancient world would ever see. They built harbor structures at Caesarea Maritima, at Puteoli, at Alexandria, at ports across the Mediterranean, all using pozzolan concrete mixed with seawater. The structures were so durable that Roman engineers stopped worrying about maintenance. They built once, correctly, and moved on to the next project. Pliny the Elder documented pozzolan in his Natural History in 77 AD, describing it as a dust that when mixed with lime and thrown into the sea, immediately becomes a single stone mass, impregnable to waves and growing stronger every day. Growing stronger every day. In 77 AD, a Roman naturalist describing 2,000-year durability using words that the 2017 American mineralogist study would confirm with crystallography 2 millennia later. The same material, the same mechanism, discovered by observation 2,000 years before the science existed to explain it. Now let me show you exactly why this works, because the materials science of Roman concrete versus Portland cement is one of the most consequential and most suppressed comparisons in the entire field of construction engineering. Portland cement, the industry standard since the 1820s, works through a hydration reaction. Calcium silicates in the cement powder react with water to form calcium silicate hydrate gel, which bonds aggregate particles together into concrete. The reaction is fast, the results are predictable, and the product is consistent. Portland cement also has 2 fundamental problems. First, the calcium silicate hydrate gel it produces is chemically unstable in the long term. In the presence of seawater chlorides, sulfates, and carbon dioxide, the gel undergoes progressive chemical degradation. It does not maintain its integrity. Second, Portland cement concrete shrinks slightly as it cures. This shrinkage creates microcracks throughout the matrix that allow water and ions to penetrate. These cracks allow elements to attack the reinforcing steel and the cement matrix itself. Portland cement concrete begins deteriorating from the moment it sets. Pozzolan concrete works by a fundamentally different chemistry. When volcanic ash is mixed with lime and seawater, a powerful reaction begins. The silica and alumina in the ash react with calcium hydroxide through a pozzolanic reaction to form calcium aluminosilicate hydrate crystals. In seawater, magnesium and aluminum ions react with components to form a crystal called philipsite and a mineral called tobermorite. Here is the extraordinary part. Tobermorite crystals do not stop growing when the concrete sets. They continue growing as long as seawater contacts the concrete. They deepen their interlocking with the aggregate matrix, filling the microcracks that would widen and fail in Portland cement. This strengthens the bond between binder and aggregate continuously over time. The 2017 UC Berkeley study examined the Caesarea Maritima harbor cores. They found interlocking tobermorite crystal clusters throughout the 2,000-year-old concrete matrix that had grown to fill virtually every crack pathway. The concrete was not just intact. The seawater exposure that would have destroyed any Portland cement structure had been continuously strengthening it. This is the distinction that the Portland cement industry cannot accommodate within its business model. Portland cement is a product engineered for predictable performance over a 50 to 100-year service life. Pozzolan concrete is a material that improves with time and requires no replacement cycle. Now here is where the story takes the turn. The construction industry has always hoped you would never reach. The global cement and concrete market generates over $600 billion in annual revenue. Infrastructure replacement driven by concrete deterioration, bridge deck replacement, highway resurfacing, seawall reconstruction, and foundation repair generates hundreds of billions more. Every dollar of that combined revenue depends on one structural reality of modern construction. Portland cement concrete has a finite service life. The average concrete highway surface requires major rehabilitation or replacement within 30 to 40 years. The average reinforced concrete bridge has a design service life of 50 years. Seawalls and coastal infrastructure built with Portland cement concrete require replacement within decades because seawater exposure accelerates the deterioration. The global infrastructure replacement market that Portland cement's deterioration schedule generates is enormous, and it is predictable. Infrastructure built today generates the replacement contract in 50 years. Infrastructure built in 1970 is generating replacement contracts right now. The entire construction engineering sector is organized around this replacement cycle. A material that builds harbor structures lasting 2,000 years without replacement disrupts every component of that organization simultaneously. Pozzolan volcanic ash cannot be patented. It is a geological material. Multiple varieties exist in deposits across Italy, Greece, Turkey, Iceland, the American Pacific Northwest, and dozens of other regions worldwide. Any construction company that wanted to use it could source it without licensing. The Portland cement industry addressed this threat by ensuring through standards, bodies, and regulatory frameworks that it remained the default material. Pozzolan additions are permitted in concrete standards, but only as a partial replacement at percentages that maintain dependence on Portland cement. Full pozzolan replacement of Portland cement in Roman-style concrete is not covered by any major construction standard. No engineering firm can specify it because no liability insurance covers it. No engineer will recommend it because their professional training covered Portland cement and not Roman concrete. The material that lasts 2,000 years is not blocked. It is simply invisible in every professional context where construction decisions are made. But here is what the Portland cement industry's control of professional standards and engineering curricula could not accomplish. It could not erase the physical evidence. The Roman concrete structures are still standing. Anyone can visit the Pantheon. Anyone can examine the harbor structures at Caesarea Maritima. The scientific literature documenting why they are still standing is published and accessible. The 2017 American Mineralogist study by Marie Jackson and her colleagues at UC Berkeley was widely covered in scientific media. It generated significant discussion in engineering and materials science communities. Dr. Jackson's research has continued to characterize the specific volcanic ash compositions and seawater interaction mechanisms. These mechanisms produce tobermorite growth, providing the mechanistic framework for reproducing Roman concrete performance. Several experimental construction projects have demonstrated that modern pozzolan concrete performs as the historical and scientific record predicts. A research team at MIT's Concrete Sustainability Hub has published work demonstrating that volcanic ash, partial replacement of Portland cement, at percentages higher than current industry practice, maintains structural performance while dramatically extending service life projections. A researcher in Iceland documented in 2019 that ancient Norse structures built with volcanic basalt lime mortar showed significantly lower deterioration rates. This was after centuries of North Atlantic weather exposure compared to equivalent structures rebuilt in the 20th century with Portland cement. The replacement buildings built with modern materials required repair within decades of construction. The original structures, built with local volcanic material, remained structurally sound. The evidence is in the harbor at Caesarea. The evidence is in the dome of the Pantheon. The evidence is in the crystallography journals. The only place it is not is in the Portland cement standard that every engineer in every country trains against. Here's exactly what to apply from this knowledge for home construction, repair, and improvement projects. The full Roman concrete formula for harbor construction is beyond the scope of most home applications, but the principles translate directly into concrete practices that any homeowner or DIY builder can implement. Here's what you need. Number 1, natural pozzolan material. Sources vary by region. In regions with volcanic geology, local volcanic tuff, pumice, or volcanic ash from geological deposits is the historically authentic material. In the United States, Class N natural pozzolans, including volcanic ash, diatomaceous earth, and calcined shale, are classified in ASTM C618. These are available from concrete admixture suppliers. Pumice, the most widely available natural pozzolan for homeowners, is sold at garden centers. Agricultural suppliers and specialty concrete retailers sell it for approximately $2 to $5 per pound. Number 2, Portland cement or lime, depending on the application. For seawater exposed applications mimicking Roman harbor concrete, lime-based binders with pozzolan replacement produce the best long-term performance. For general construction applications, replacing 20 to 40% of Portland cement with natural pozzolan maintains equivalent early strength. This significantly improves long-term durability and reduces thermal cracking. Number 3, aggregate and water as for any concrete mix. Here is the application guidance. For any concrete project involving ground contact, water contact, or seawater exposure. Replacing 30% of the Portland cement with pumice dramatically reduces the chloride ion permeability that leads to reinforcing steel corrosion. This extends the service life of the structure. For lime mortar repair of historic masonry, adding 20 to 30% pumice is key. It creates a hydraulic lime mortar that sets harder and resists water penetration better than plain lime mortar. This closely approximates the performance of historic Roman mortars used in structures that have survived centuries of weather. For concrete footings, retaining walls, and foundations in contact with soil, the pozzolan replacement reduces the calcium hydroxide content. This prevents the sulfate attack failure mode that shortens foundation service life. The total material cost difference between standard Portland cement concrete and pozzolan modified concrete is negligible. Pumice costs approximately $2 to $5 per pound and replaces an equivalent weight of Portland cement at a similar price point. The performance difference over a 50 to 100 year service horizon is not negligible. It is the difference between the infrastructure the Romans built and the infrastructure we keep replacing. Some knowledge does not disappear because it failed. It disappears because the replacement cycle built around its inadequate substitute cannot survive its common adoption. The Roman engineer who first mixed Puteoli volcanic ash with lime and seawater in the 2nd century BC was not a material scientist. He was a builder who needed concrete to set underwater and who discovered, through the empirical testing that all builders perform, that the gray dust from the Campi Flegrei volcanic field produced something that nothing else could. He did not know about tobermorite, he did not know about pozzolanic reaction or crystal growth mechanisms or aluminosilicate hydrate phases. He knew that his harbor structures were not falling down and that the same structures built with other materials were. He passed that knowledge to the next builder, and the next, and the next, for 4 centuries of Roman construction practice that built the most durable infrastructure in the history of human civilization from a material that costs $2 per pound and grows stronger in seawater. The 2017 crystallography team that published the American Mineralogist paper did not discover anything the Romans did not already know by observation. They discovered why it worked. They described the crystal growth mechanism that Pliny had described as growing stronger every day without the vocabulary to explain how. The Pantheon does not need the mechanism to be described in order to stand for another 2,000 years. It only needs the volcanic ash and the lime and the seawater that have been producing tobermorite crystals inside its concrete for 19 centuries and show no sign of stopping. Portland cement lasts 50 years and requires replacement. Pozzolan concrete lasts 2,000 years and requires none. The construction industry needs you to keep building with the one that requires replacement. The volcanic ash does not. If this vault changed how you look at the crumbling concrete driveway, the deteriorating foundation, or the seawall that needs replacement again, 20 years after the last one, subscribe and share this with someone who deserves to know that the ancient powder that solved this problem 2,000 years ago costs $2 per pound and is waiting at the same geological deposit where the Romans found it. The next vault opens soon.